For most of human history, buildings had to work with their local climate because they had no other choice. Thick adobe walls in the desert, steep roofs in snowy mountains, elevated huts in the tropics. These were intelligent, evolved responses to place. Then, for a brief century, we thought we could out-engineer nature with cheap energy and powerful machines. We built the same glass box in Dubai, Denver, and Dublin. That era is over. Climate-responsive design is the return to first principles, but supercharged with modern science and materials. It's the philosophy that a building should be its own first line of defense and comfort, intuitively responding to sun, wind, and rain. Let's explore how this works across the world's major climate zones. The foundation is solar geometry and orientation. This is non-negotiable. In the northern hemisphere, the long axis of your building should typically run east-west. This maximizes southern exposure for winter sun and minimizes harsh eastern and western low-angle sun. But the strategy diverges radically from there. In a cold climate, you're a solar farmer. You want to capture and store that low winter sun. This means large south-facing glazing, coupled with high thermal mass materials like concrete or masonry floors inside to absorb the heat during the day and release it at night. The envelope is super insulated and airtight to trap that free heat. The form is often compact to reduce surface area and heat loss. A pro tip for cold climates: use a roof overhang calculated to block the high summer sun but admit the low winter sun. It's a fixed, passive shading device designed by the Earth's tilt. Now, flip to a hot-arid climate like the desert. Here, the sun is the enemy, but the massive diurnal temperature swing. Hot days, cold nights is your friend. The traditional strategy is massive, thermally heavy walls. Think adobe or rammed earth. These walls absorb heat all day, slowing its passage to the interior. By the time heat tries to migrate in at night, the outside air has cooled, and the process reverses. Windows are small and shaded. Courtyards are crucial, providing a cool, shaded outdoor oasis that also induces stack ventilation. The modern interpretation uses insulated walls with external insulation and exterior fixed shading, like deep brise soleil. In a hot, humid climate, the strategy is opposite. Thermal mass is a liability because nights don't cool down enough to purge the heat. The goal is to maximize ventilation and provide shade. Buildings are light, often elevated on pilots to catch breezes, with large operable windows on opposite sides for cross-ventilation. The roof is a big, lightweight umbrella with wide overhangs. Materials are breathable. The form can be elongated to catch prevailing winds. Here, the porch or veranda is the essential transitional space. A shaded, semi-outdoor room. For temperate and mixed climates, the building must be adaptable, a seasonally responsive machine. This is where dynamic elements come in: operable shading, high-performance glazing that changes properties, and hybrid ventilation systems. The building envelope is highly insulated but has ample operable windows for when natural conditions are perfect. The form often includes sunspaces or enclosed porches that can be opened up in summer and closed off as a thermal buffer in winter. The key is designing for the shoulder seasons, not just the extremes. Finally, rain and storm responsiveness. In wet climates, the building should shed water gracefully. This means deep overhangs, generous roof pitches, rain screen cladding that allows walls to dry, and careful detailing of flashings. In storm-prone areas, the form should be aerodynamic, with strong, continuous load paths tying the roof to the foundation. Climate-responsive design isn't a style, it's a logic. It asks, "Where am I?" and then listens to the answer provided by the sun path, the wind rose, and the rain gauge. The result is a building that feels inherently rooted, comfortable, and resilient long before you ever touch a thermostat.